Heyo, what's up guys? Baby Bear 4812 coming at you one more time. Today, doing problem 74 called Search a 2D Matrix. Super liked problem, hella popular, Amazon, Microsoft, Facebook, Bloomberg, all the big guns are asking it, and we're going to cover it. So, for those of you not familiar with the question yet, essentially it just says that we need to write an efficient algorithm that will search for a specific value in a m by n matrix. This matrix has the following properties, and so it tells us that integers in each row are sorted from left to right, and that the integer of each row is greater than the first integer of each row is greater than the last integer of the previous row. So we look at an example like this one, we could see that the row is sorted, okay, so increasing numbers, and it says that specifically this number here, so the first entry of the nth row is greater than the last entry of the n minus 1th row, or I minus 1. If the target is 3, we would output true in this case because we found a 3. If the target is 13, we would output false because, as you can tell, we do not have a 13 in here. Pretty straightforward. Now, a couple ways to approach this problem, and I know what y'all are thinking because I thought the same thing. Well, Baby Bear, can't I just loop through the numbers and solve this problem linearly? Just walk through the whole array. The answer is yes, you can. However, one, not the most efficient solution. Two, your interviewer is not going to be a happy camper with you if that's the only solution that you propose. So you can tell them this is kind of like the obvious dumbed down way to do it, but we can do better. And so let's think about how in particular we could do better. Well, you know, we're told one thing. We're told that that it's sorted in increasing order. They're sorted from left to right, and that each row is bigger than the next. So how do we search for numbers inside of an array typically, or a list when it's sorted, right? So let's think about it. It starts with a B, rhymes with binary. I heard you say it, you got it, that's right, binary search. So we're gonna need to do some sort of evolved equivalent of a binary search and adapt it to a 2D matrix. So let's think about how we're gonna do that here. I'll go over to my sketchpad, and I kind of realized would have been nice of me to have written this out quicker for you, but no matter. 11, and we had, oh boy, I'm sorry guys. 16, I'm gonna make these up, 22, 30, 35, and 42, everyone's favorite number. Okay, so let's pretend this is our matrix, and you know, we've got our target is going to be, let's see, we're looking for the number 3. Okay, target equals 3. So what do we do here? How do we go about actually finding a 3? Well, like I said, we're not going to do that the caveman solution, as I like to call it, of just walking through the whole array. We're going to try to do this in a binary search fashion. The reason we do that is because that brings us down to logarithmic time instead of linear time. And I've mentioned this in other videos, but it's important to remember that the difference between, you know, log of n time to n time is exponential, right? Because we'd have to, it's kind of like going from from linear to exponential. There's literally an exponential difference, and so is the difference from the logarithmic to the linear. So in super big matrices, this does definitely make an important difference. So in a typical binary search, we set up a left and right pointer, and you know, if we're looking at this array, we set up a left and right pointer, and we tell ourselves, okay, well, I'm going to check what the middle term is here. In this case, it would kind of fall here. Then I ask myself, relative to my target, is my middle term greater than the target, less than, or equal to? If it's equal to, cool, let's return it. We'll return true, whatever we got to do with it. If not, we'll shift either our left or right pointer to either side of that middle in order to then search only either the left or the right half of the array. So we are going to employ that here as well, but even as a precursor to doing that, we're gonna have to first identify the row that it exists in. So our first step is actually going to be to find the row that we need. Our second step, once we find that row, we're gonna search that row. And both of these steps we're going to do in a binary search fashion. So, for instance, if I'm going to start by calling this, maybe I'll call this top and I'll call this bottom. Of course, this is a bit of a smaller, shorter example, so middle is kind of trivially here. But the question becomes, how do I know if this is my row or not? Can I stay in this middle row? Do I need to go up? Do I need to go down? What do I do? Well, we're told that we know the relationship between this number and this number, or rather this number and this number. We know that since these are all increasing, and that the 10 here has to be strictly greater than the 7, and the 22 is strictly greater than the 20, and so on, we can simply ask ourselves, well, does this target fall within, in the range of here to here? If it does, if it's between those two numbers, or equal to them, cool, we're gonna stay here, we found our row. If it's not, so if this target is smaller than our first entry, which in this case it is, surely we've gotta start searching up above. I was gonna say, and don't call me Shirley, but that would have been too easy. Otherwise, so in this case, the 3 is definitely smaller than the 10. So we're going to say, okay, let me binary search upward. So everything here and below is gone. We're going by Charlie with that. If this target was 30, for instance, we would say, okay, well, it's not in this range between between 10 and 20. In fact, we're going to compare it to the extremes of our array, and we're noticing it's greater than the end of the array. So it must be somewhere in the lower half of this two-dimensional array. I hope that makes sense. I don't think this one is kind of too logically difficult. We've definitely worked through more involved problems, but there may be a couple nuances in the code when we go through the implementation. So yeah, I think we're in a good spot to kind of, like I said, logically, I think this makes sense. Again, if it doesn't, let me know in the comments down below. But let's jump into the code and see what we can do about it there. So this will be a bit longer, so I'll kind of move this over here right off the bat. First thing I want to do is my standard error checking. So maybe we'll break it down. So we'll do error checking, and then we say we need to find row, and then we want to search row. Those are our 3 main steps. Well, for the error checking portion, we can simply go if not matrix. So if we're given an empty matrix, or target is none. So the target, we can't say is not target, or not target. This would be an issue because it would return truthy if target was 0. So the reason I'm saying none specifically is if I really just don't get a value for it. Or target is none. In that case, we want to return false. Okay. Now, to find the row, maybe we'll do something like, I'll say row is equal to self.find row. We'll just to modularize the code. We can write a function for that. And in it, we're definitely going to have to pass the matrix and the target. Finally, we want to search that row. And so we'll say, maybe within searching that row, we can actually just return a Boolean value as to whether or not we found it. So I'll just say return self.search row, and we're going to want to pass in that row, so that'll be matrix of this row that we calculate here, which will be some integer and the target itself. So this is actually just going to be a standard binary search. I could call it binary search. It doesn't really matter. I think you guys get it. So this is our little kind of main function, and then I'll write the helpers now. So the first one we're going to need to write is find row. So I said we'll define find row. We got self, matrix, and target. I'll try pass there for now as I'll I'll define the second one as well, just so we kind of we have it here. Something for whatever reason that I like to do. I find that it helps me organize my thoughts, so I'm sharing it with you guys. Now, we want to find the actual row here. Okay. Well, let's think about this. We're gonna have, I'll call these top and bottom instead of left and right like we do in the standard binary search. So I'll call it top row 0, and you kind of imagine this is our top row, and this will be our bottom row. So I think that nomenclature should make sense. And bottom, like I said, will equal, call it the length of the matrix, minus 1. Right? Length, yes. Okay. Now, what we're going to want to do is we're going to say, while the bottom is greater than the top, right? So the bottom one, again, in this case would be 2, and top would be 0. So while we still have some gap there, we're going to want to first calculate our mid. So mid is equal to, and I've shown you guys this before, we can just do top plus bottom divided by 2 because we're looking for an average. However, if these two numbers are super big, we might run into an integer overflow issue. So we can write an equivalent, which is bottom minus, bottom plus top minus bottom. And what this is just literally some fraction manipulation. If you write this out, you can prove it to yourself that the math checks out that it's equivalent. Now, we're going to need to check certain conditions to see whether or not our target number actually falls within this row. And I think the easiest way to check this is as follows. We could simply say that if our target is greater than or equal to our matrix in the row we're looking at, that mid row, if it's greater than or equal to the first element of that row, so if it's greater than or equal to the smallest element of that row, and it's less than or equal to the greatest element, then it must exist in that row, right? So say if target is greater than or equal to matrix mid of 0, and target is less than or equal to matrix at mid of our last element, so -1, then in that case we're going to return mid. We're happy with that row, that's one we like. Otherwise, let's say, let's say our target's not in that range and we find that the target is greater than the end of the array. So maybe target is greater than, than the range of numbers in that row. So I'll say if target is greater than matrix of mid at -1, then what we want to do is we want to say, okay, I got to search downwards. So I'm going to take my top row and I'm going to bring it to below where my mid was. So I'm going to say, take the top row and set that equal to whatever mid was +1. Because again, we want to take it from the top and bring it downwards because we now want to search the bottom half, okay? Finally, we can do an else statement here, but just to spell the logic out, if the target is less than matrix of mid at 0, so if it's smaller than everything in that range, we're going to want to take our bottom row and bump it up above the mid so we can search the top half of our array. So say bottom is equal to mid -1. At the end of this, we can simply return whatever bottom, whatever bottom's pointing at, like we would in a standard binary search. So this is our first helper function. It's going to tell us what row our target may potentially exist in, right? So far so good. And I will also add that, you may end up in a situation where the target just doesn't exist outright. And maybe if you'd like, you can check that in your errors here at the start and say if the target is kind of less than this first number and greater than the largest number, then let's not even bother doing any of this. I'm omitting that check here just kind of for simplicity, but you can definitely do that. So I'm aware that it may not be in this range, but this will still work regardless. Now, so we've done this find row. Now we need to implement the binary search within the actual row itself. So from here, it's for the most part steady sailing. We'd have something like left is equal to 0, right is equal to row, which is now an array. So the length of the row -1. And we'll do a binary search. And, one thing, the reason I left the space here is as follows. We do need to do a quick error check here as well. Because what if we're given an empty array, right? And in one of the test cases, you'll see this. I'm telling you this because I messed it up. But you could just have one empty array nesting in here, or nested in the larger one. So we do need to say that if not matrix, then return false. Again, we're returning a Boolean value here. So a bit administrative, but has to be done. Next, we can say while left is less than, or right, or rather, I'm going to say less than or equal to here. And the reason I'm gonna do that is because I still do wanna check that final overlap of the two numbers, just to really make sure that that we're gonna find that number. Because if it kind of sits on the left pointer, but we're not returning the pointer at the end, we'll never really find it if we don't check when those overlap. Let me know if that makes sense. I'm happy to explain it down below if I kind of fudged that explanation a bit. So we'll do the same thing here. We'll say mid is equal to left plus, say, whoops, it's not a plus, plus right minus left divided by 2. And then we'll do as follows. We'll say if, what is that? If row of mid equals target, so we've hit the nail on the head, we're going to return true. Otherwise, if our middle point is greater than the target, if it's greater than the target, then we need to search on the left half of the array, right? So the point that we're looking at is too big. We got to go smaller. We got to think smaller. If we think smaller, we go to the left-hand side. So I'm going to say that right is going to be equal to mid minus 1, so we shift that all to the left. Otherwise, and again, I know I can simplify this here to an else statement, but I really want to spell out the logic. Otherwise, if row of mid is less than the target, we need to start thinking bigger. So I got to take my left pointer, set it equal to mid plus 1, so we can check the right-hand side of the array. If all fails, we didn't find anything, we go home empty-handed, we return false. Standard binary search, like I said. 2 standard binary searches, really. That's 4. 2. And that should be it, guys. I'm going to run this just to make sure that I didn't make a silly, which I did. And it looks like I made a silly on line 18, if not matrix, or we called it row here. So that'll do it. Should be good. We hit submit. Ta-da. All right, so that's it. As a quick recap, all we said was let's do an error check. Let's find the row that we need to exist, where target may potentially exist, and then let's search that row for that target number. This is all going to run in logarithmic time because we're applying a binary search. This problem is possible with a linear walkthrough, which is super vanilla, boring, and not going to get you a job at, drumroll please, Amazon, Microsoft, Facebook, or Bloomberg. But this solution will. Okay? So I hope you guys enjoyed it. Any questions, as always, let me know down below. Let me know what you'd like me to answer next. If you have anything that just itch in your mind that you can't figure out. Apart from that, the good stuff. Like, subscribe, share with your friends. Tell your mom, tell your grandma, tell everybody about the channel. It would go a long way. And yeah, let me know how I can help you guys next in any capacity, and I'll make it happen. And I'll see you next time. Peace.